On the morning of September 14, 1967, 5 railroad engineers crossed the Devil's Canyon Bridge in New Mexico for what should be a routine inspection. By 11:47 a.m., all 5 men plunged 300 feet to their deaths when the century-old steel structure catastrophically fails beneath them. 5 families lose their husbands and fathers. An entire community mourns, all because a critical support beam, weakened by decades of desert winds and neglect, finally surrenders to forces it can no longer withstand. If you want to understand how this tragedy claimed 5 lives and changed railroad safety forever, subscribe to this channel. This episode is a fictionalized reconstruction inspired by real transportation accidents and transit safety investigations. Names, locations, and specific events have been created for storytelling purposes. The Devil's Canyon Bridge stretches across one of New Mexico's most unforgiving landscapes, a steel monument to 19th-century engineering ambition. Built in 1889 by the Santa Fe and Western Railroad Company, this massive truss bridge spans 850 feet across a jagged canyon that drops nearly 400 feet to a rocky riverbed below. The structure towers 320 feet above the canyon floor, its latticed steel framework casting intricate shadows across red sandstone walls that have stood for millennia. September in northern New Mexico brings scorching days and frigid nights, with temperatures swinging 40 degrees between dawn and dusk. The desert air carries the scent of sage and creosote, mixed with the metallic tang of aging steel and the acrid smell of railroad ties soaked in preservative oil. Wind constantly howls through the canyon, creating an eerie whistle as it passes through the bridge's steel members. On this particular morning, that wind gusts to 35 miles per hour, rattling loose bolts and causing the entire structure to sway almost imperceptibly. The bridge serves as a critical link in the transcontinental freight network, carrying dozens of heavy trains each day between California ports and eastern markets. Coal trains from Colorado, container ships cargo from Long Beach, grain cars from Kansas wheat fields, all depend on this single span across Devil's Canyon. The railroad considers it indispensable, despite growing concerns about its age and condition. Local residents have grown accustomed to the thunderous rumble of locomotives crossing overhead, a sound that reverberates through the canyon like rolling thunder. By 1967, the bridge shows its age in countless ways. Paint peels from steel members, revealing patches of rust that spread like cancer across critical joints. Bolts work loose from constant vibration, and several have fallen to the canyon floor over the years. The wooden deck planks, replaced numerous times, show gaps where boards have warped and shrunk in the desert climate. Railroad workers joke nervously about the bridge's longevity, calling it Old Faithful, with a mixture of affection and apprehension. The Santa Fe and Western Railroad Company has owned and operated the Devil's Canyon Bridge for 78 years by September 1967. Company records show a troubling pattern of deferred maintenance and cost-cutting measures that have affected the structure's integrity over decades. The railroad industry faces intense competition from trucking companies and faces pressure to minimize expenses wherever possible. Bridge maintenance, expensive and disruptive to operations, often gets delayed or reduced in scope. Federal railroad safety regulations in 1967 remain relatively basic compared to modern standards. The Interstate Commerce Commission requires periodic inspections but provides little specific guidance about structural analysis or load testing. Most railroads rely on visual inspections by company engineers, supplemented by occasional visits from consulting firms. The Santa Fe and Western follows this minimal approach, conducting annual walkthrough inspections but rarely performing detailed structural analysis. Previous incidents at Devil's Canyon Bridge have raised red flags that company management has largely ignored. In 1962, a locomotive derailment on the bridge damaged several cross braces, repairs that were completed quickly but without comprehensive structural assessment. 3 years later, high winds caused visible swaying that prompted temporary speed restrictions, but no engineering study followed. Workers have reported loose bolts, cracked welds, and unusual sounds during train crossings, but these concerns rarely reach senior management. The bridge's maintenance history reveals a pattern of reactive rather than preventive care. Company records show repairs made only when problems become obvious or when equipment failures force action. Painting schedules stretch longer than recommended, allowing rust to establish footholds in critical areas. Bolt replacement happens sporadically, usually after workers notice missing hardware. The most recent comprehensive structural assessment occurred in 1954, 13 years earlier, and recommended extensive repairs that were never fully completed. Economic pressures intensify the railroad's reluctance to invest in major bridge work. The company faces declining passenger revenues as airlines capture long-distance travelers, forcing greater reliance on freight operations. Competition from interstate trucking cuts into traditional railroad cargo markets. Union negotiations demand higher wages, while shareholders expect maintained dividends. In this environment, bridge maintenance competes with more visible priorities like new locomotives and expanded rail yards. Training programs for bridge inspectors remain informal and inconsistent in 1967. Most railroad engineers learn inspection techniques through apprenticeship rather than formal education. Company standards exist on paper, but vary widely in implementation. Inspectors often lack specialized knowledge about fatigue analysis, load calculations, or non-destructive testing methods that could identify hidden structural problems. The emphasis remains on keeping trains moving rather than identifying potential safety issues. The 5 men who will lose their lives on September 14th represent decades of combined railroad experience and deep knowledge of bridge operations. Chief Inspector Robert Martinez, 52, has worked for Santa Fe and Western for 28 years, rising through the ranks from track laborer to senior engineer. Martinez earned respect throughout the company for his meticulous attention to detail and unwillingness to compromise on safety issues. He leaves behind a wife and 3 children, including a son who recently started college. Senior bridge engineer Thomas Chun, 45, joined the railroad after serving in the Army Corps of Engineers during World War II. His military experience with bridge construction and demolition made him invaluable for complex structural assessments. Chun has inspected the Devil's Canyon Bridge dozens of times over his 15-year career with the company. His colleagues know him as methodical and thorough, someone who takes extensive notes and photographs during every inspection. He has 2 daughters and coaches Little League Baseball in his spare time. Assistant Inspector David Williams, 38, represents the new generation of railroad engineers, holding a civil engineering degree from New Mexico State University. Williams brings modern analytical techniques to bridge inspection, often advocating for more sophisticated testing methods than company policy requires. His youth and education sometimes create tension with older inspectors who rely more on experience than formal training. Williams married his college sweetheart 2 years ago and recently bought their first house. Maintenance Supervisor Frank Santos, 41, oversees the crew responsible for bridge repairs and routine upkeep. Santos knows every bolt, beam, and connection on the Devil's Canyon Bridge from years of hands-on work. His practical knowledge complements the engineer's theoretical understanding, providing insight into how the structure actually behaves under different conditions. Santos has worked railroad bridges across the Southwest and considers Devil's Canyon among the most challenging due to its age and exposure to harsh weather. He has 4 children and volunteers as a volunteer firefighter. Junior engineer Michael Rodriguez, 29, recently completed his probationary period and earned permanent status with the company. Rodriguez shows enthusiasm for learning and often volunteers for challenging assignments like the Devil's Canyon inspection. His fresh perspective sometimes identifies problems that more experienced eyes might overlook. Rodriguez moved to New Mexico from Texas to take the railroad job and still feels like an outsider in the tight-knit community. His wife is pregnant with their first child. September 14, 1967, begins like countless other days at the Santa Fe and Western Railroad's Albuquerque Division headquarters. The overnight dispatcher's report shows normal freight traffic across the system, with no weather alerts or operational problems requiring immediate attention. The Devil's Canyon Bridge carried its usual complement of trains during the previous 24 hours, including 2 heavy coal drags and a high-priority container train from California ports. Weather conditions appear favorable for the scheduled bridge inspection, with clear skies and moderate temperatures forecast. However, the National Weather Service issues a wind advisory for the region, predicting gusts up to 40 miles per hour throughout the day. Such winds are common in September as seasonal weather patterns shift, but they can make bridge work more challenging and dangerous. The inspection team reviews the forecast, but decides conditions remain within acceptable limits for their planned activities. Equipment readings from the railroad's signal systems show normal operations across the Devil's Canyon section. Automatic block signals function properly, track circuits indicate clear rails, and communication systems operate without problems. The bridge's load monitoring equipment, installed in 1961 after the derailment incident, shows stress readings within normal ranges for typical train traffic. However, this equipment only measures gross structural response and cannot detect localized problems in individual members. The inspection team gathers at 7:30 a.m. for their pre-work briefing, reviewing safety procedures and discussing the day's objectives. Company policy requires comprehensive annual inspections of all major bridges, with Devil's Canyon scheduled for its 1967 assessment. The team plans to examine the structure systematically, starting with the eastern approach and working westward across the span. They carry standard inspection equipment including measuring tools, cameras, and sample containers for any materials that might require laboratory analysis. Martinez emphasizes safety protocols during the morning briefing, reminding team members about fall protection requirements and communication procedures. The inspection will require walking across the bridge deck and climbing down to examine lower structural members, activities that pose significant risks given the structure's height and the canyon's windy conditions. Each team member checks his safety equipment and confirms radio contact with the dispatcher who will coordinate train traffic during the inspection. Maintenance records from the previous week show routine activities on the Devil's Canyon Bridge, including replacement of several loose bolts and minor repairs to deck planking. Santos supervised this work personally, noting in his report that some bolts appeared to have been loose for extended periods based on wear patterns around the holes. He recommended more frequent bolt inspections, but did not identify any immediate safety concerns. The work crew reported hearing unusual sounds during their activities, but attributed them to normal structural response to wind loading. Train traffic logs reveal heavy usage of the bridge in recent days, including several overweight loads that required special handling. Railroad operating rules allow such loads when they remain within the bridge's rated capacity, but the cumulative effect of repeated heavy trains can accelerate fatigue damage in aging structures. The most recent heavy load crossed just 18 hours before the scheduled inspection, a coal train with locomotives and cars totaling nearly 8,000 tons. Communication between the inspection team and railroad dispatch confirms that train traffic will be suspended across Devil's Canyon Bridge from 9 a.m. until the inspection team declares the structure safe for resumed operations. This standard procedure ensures inspector safety while allowing thorough examination of all structural elements. However, the pressure to complete inspections quickly and restore service creates subtle but persistent time pressure on inspection teams. Weather monitoring equipment at nearby stations begins recording increasing wind speeds as the morning progresses. By 8:30 a.m., sustained winds reach 25 miles per hour with gusts approaching 35 miles per hour. These conditions remain within the railroad's guidelines for bridge inspection activities, but they make the work more difficult and potentially more dangerous. Wind-induced vibrations can mask structural problems while creating additional stresses on aging components. The inspection team departs for Devil's Canyon Bridge at 8:45 a.m., traveling by railroad truck along service roads that parallel the track. The 15-mile journey takes them through increasingly rugged terrain as they approach the canyon. Desert vegetation gives way to exposed rock formations, and the landscape takes on the stark beauty that characterizes much of northern New Mexico. The men discuss their inspection strategy during the drive, with Martinez assigning specific responsibilities to each team member. At 9:15 a.m., the team arrives at the eastern approach to Devil's Canyon Bridge and begins unloading their equipment. The structure looms ahead of them, its steel framework silhouetted against the morning sky. Wind whistles through the canyon below, creating the characteristic sound that locals have heard for decades. The men can feel the bridge vibrating slightly under wind loading, a normal response that nonetheless serves as a reminder of the forces constantly acting on the aging structure. Initial visual inspection from the eastern abutment reveals several obvious maintenance issues that require documentation. Paint deterioration is extensive across much of the structure, with rust clearly visible on numerous members. Several bolts show signs of loosening, and gaps appear in some connections where thermal expansion and contraction have caused movement over the years. These problems are typical for a bridge of this age and exposure, but they indicate the cumulative effects of decades of deferred maintenance. The critical failure that will lead to 5 deaths begins in the bridge's lower chord, a massive steel member that carries tension forces from the structure's dead weight and live loads. This member, designated as L7 in the original construction drawings, spans 120 feet between vertical supports and carries some of the highest stresses in the entire bridge. Over 78 years of service, repeated loading cycles have created microscopic cracks in the steel that gradually propagate through the member's cross-section. Fatigue cracking in steel structures occurs when repeated stress cycles cause small flaws to grow over time, eventually reaching critical dimensions where the remaining material can no longer carry required loads. The process is invisible to casual observation and often undetectable without sophisticated testing equipment. In 1967, railroad bridge inspectors lack access to ultrasonic testing, magnetic particle inspection, or other non-destructive methods that could identify such problems before they become critical. The L7 lower chord member experiences particularly severe fatigue conditions due to its location and loading patterns. Every train crossing the bridge creates stress cycles as locomotive and car weights pass overhead. Heavy trains cause higher stresses, while lighter trains create smaller but still damaging cycles. Wind loading adds additional stress variations, and temperature changes cause thermal stresses that further contribute to fatigue damage. Over nearly 8 decades, millions of stress cycles have accumulated in this critical member. Manufacturing practices in 1889 inadvertently created conditions that accelerate fatigue damage in the L7 member. The steel contains impurities and inclusions that serve as crack initiation points, and fabrication techniques of the era created stress concentrations at connection details. Riveted connections, state-of-the-art in 1889, create complex stress patterns that can promote crack growth. Modern welding and steel production methods would have produced a more fatigue-resistant structure, but such technologies did not exist when Devil's Canyon Bridge was built. Environmental factors unique to the desert Southwest have accelerated deterioration of the critical member. Wide temperature swings between day and night create thermal stresses that supplement mechanical loading. Blowing sand acts as an abrasive, gradually wearing away protective paint and exposing steel to corrosion. Low humidity prevents the formation of protective oxide layers that might slow corrosion in other climates. These factors combine to create particularly harsh conditions for steel structures. Recent heavy train traffic has pushed fatigue damage in the L7 member toward its critical threshold. The coal trains that crossed during the previous week created some of the highest stress levels the bridge has experienced in months. Each passage advanced existing cracks by microscopic amounts, bringing them closer to the critical size where sudden failure becomes inevitable. Unknown to anyone, the structure is now operating with significantly reduced safety margins. At 10:30 a.m., the inspection team begins its systematic examination of the bridge structure, starting with the deck and working downward through the truss members. Martinez leads the team across the bridge deck, noting areas where planking needs replacement and documenting bolt conditions at each connection point. The men work methodically, aware that thoroughness is essential but also conscious of the need to complete their work and restore train service. Wind conditions continue to intensify as the morning progresses, with gusts now reaching 40 miles per hour. The bridge responds to these loads with increased vibration and movement, making the inspection work more challenging and potentially more dangerous. Team members must maintain secure footing on narrow walkways while handling tools and equipment. Communication becomes difficult as wind noise overwhelms normal conversation. Chen begins photographing structural details that show signs of deterioration or unusual wear patterns. His camera captures images that will later prove crucial to understanding the failure sequence, though their significance is not apparent at the time. The photographs document rust patterns, bolt conditions, and connection details throughout the structure. Chen's methodical approach ensures comprehensive documentation, but the process takes considerable time. Williams conducts measurements of structural deflections and joint movements, comparing his findings to previous inspection reports. Some measurements show changes from earlier inspections, indicating ongoing structural adjustments as the bridge ages. While these changes appear gradual and within expected ranges, they reflect the cumulative effects of decades of loading and environmental exposure. Williams notes several measurements that warrant further monitoring in future inspections. Santos examines connection details and hardware conditions throughout the lower portions of the structure. His practical experience allows him to identify problems that might escape notice during cursory inspections. Santos finds several connections where bolts have worked loose, gaps where thermal movement has opened joints, and areas where corrosion has progressed more rapidly than expected. Each finding gets documented for follow-up maintenance activities. Rodriguez assists other team members while gaining experience with bridge inspection procedures. His fresh perspective proves valuable in identifying details that more experienced inspectors might overlook due to familiarity with the structure. Rodriguez notices several areas where paint failure has exposed steel to accelerated corrosion, and he documents connection details that show unusual wear patterns. At 11:35 a.m., the team reaches the critical section of the bridge where the L7 lower chord member carries maximum stress loads. The member appears normal during visual inspection, with no obvious signs of distress or damage. Paint covers most of the surface, hiding the internal crack that has grown to critical dimensions. The men examine connection details and measure deflections, unaware that catastrophic failure is imminent. Wind gusts reach their peak intensity as the inspection team works in the most critical area of the structure. The sustained 40-mile-per-hour winds create dynamic loads that supplement the deadweight stresses already present in the lower chord member. These additional stresses push the cracked member beyond its remaining capacity, initiating the final phase of the failure sequence. The catastrophic failure begins at 11:43 a.m. when the crack in the L7 lower chord member suddenly propagates through the remaining steel cross-section. The failure occurs with explosive violence as stored elastic energy in the member is released instantaneously. The sound of tearing steel echoes across the canyon, audible over the howling wind. Within seconds, the loss of this critical member triggers a progressive collapse sequence that will claim 5 lives. As the L7 member fails, loads that it was carrying redistribute to adjacent structural elements that are not designed to handle such forces. These secondary members begin failing in rapid succession, creating a cascade of structural collapse that spreads throughout the affected span. The bridge deck begins to sag as its primary support system disintegrates, tilting at increasingly steep angles as the collapse progresses. Martinez recognizes immediately that the bridge is failing catastrophically and shouts warnings to his team members. The men attempt to reach safety, but the collapse sequence progresses too rapidly for escape. The deck section where they are working tilts beyond the angle where footing is possible, and the men lose their grip on the increasingly steep surface. Safety equipment that might have helped in other circumstances proves inadequate for the extreme conditions of total structural collapse. Chun tries desperately to reach a vertical support member that might provide secure attachment for his safety line, but the distance proves too great as the deck continues tilting. Williams and Rodriguez attempt to help each other maintain position, but the collapsing structure makes coordinated movement impossible. Santos recognizes that the failure is spreading toward the eastern abutment and tries to move in that direction, but the deck's increasing angle makes progress impossible. The failed section of bridge drops away from its supports with the 5 men trapped on its surface. The massive steel and timber structure plunges 300 feet toward the canyon floor, carrying the inspection team with it. The men are unable to escape the collapsing structure due to the speed of the failure sequence and the extreme angles involved. Wind resistance during the fall provides no meaningful deceleration given the weight of the falling debris. The impact with the canyon floor occurs at 11:47 a.m., creating a thunderous crash that reverberates throughout the region. The twisted remains of steel beams, timber decking, and inspection equipment scatter across the rocky canyon bottom. The 5 men are overcome by the massive impact forces and do not survive the catastrophic structural collapse. All 5 inspection team members perish in the accident, their lives ended instantly by the tremendous forces involved in the bridge failure. Emergency response begins within minutes of the collapse as railroad dispatchers receive reports of the catastrophic failure from nearby residents who heard the impact. The Santa Fe and Western Railroad activates its emergency response procedures, dispatching rescue teams and medical personnel to the canyon site. However, the remote location and difficult terrain make immediate response challenging, and the scale of the structural collapse makes survival impossible. Local emergency services receive notification of the bridge collapse at 11:52 a.m. and immediately dispatch fire department rescue teams and ambulances to the scene. The volunteer fire department in the nearest town, 12 miles away, responds with specialized equipment for high-angle rescue operations. County sheriff's deputies coordinate the emergency response and begin securing the accident scene for investigation. Railroad officials arrive at the collapse site by 12:30 p.m. and quickly realize the magnitude of the tragedy. Company executives travel from Albuquerque headquarters while engineering staff begins documenting the failure scene. The railroad's insurance representatives are notified immediately, as are federal regulatory agencies that will oversee the accident investigation. Media representatives begin gathering at the site as news of the collapse spreads throughout the region. Rescue teams rappel into the canyon to reach the accident site, though the extreme nature of the collapse makes survival unlikely. The massive steel structure has created a debris field covering several acres of the canyon floor. Rescue personnel work methodically through the twisted wreckage, searching for any signs of life while documenting the positions of structural elements that will be crucial for the investigation. Recovery operations continue throughout the afternoon as specialized equipment is brought to the remote canyon site. Heavy cranes capable of lifting the massive steel beams must be transported over difficult terrain, delaying recovery efforts. The bodies of all 5 inspection team members are located within the wreckage by evening, confirming that none survived the catastrophic collapse. The immediate aftermath of the Devil's Canyon Bridge collapse reveals the full scope of the tragedy that has befallen the Santa Fe and Western Railroad and the local community. 5 experienced railroad professionals have lost their lives in an instant, leaving behind grieving families and a company struggling to understand how such a catastrophic failure could occur. The death toll stands at 5, with no survivors from the inspection team that was conducting routine safety procedures when the structure failed. Chief Inspector Robert Martinez, 52, succumbs to massive trauma sustained during the structural collapse and impact with the canyon floor. His death represents the loss of nearly 3 decades of railroad experience and institutional knowledge about bridge operations throughout the Southwest. Martinez's widow and 3 children face an uncertain future, as do the families of the other 4 victims who perish in the accident. Senior bridge engineer Thomas Chun, 45, loses his life along with his colleagues when the bridge section plunges into the canyon. His military engineering background and 15 years of railroad bridge experience made him invaluable to the company's infrastructure maintenance programs. Chin's death leaves his wife and 2 daughters without their primary source of income and emotional support. Assistant Inspector David Williams, 38, passes away in the collapse despite his youth and modern engineering education. Williams represented the future of railroad bridge engineering, bringing contemporary analytical techniques to an industry still relying heavily on traditional methods. His recent marriage and new home purchase make his death particularly tragic for his young widow. Maintenance Supervisor Frank Santos, 41, perishes along with his inspection team colleagues. Santos's hands-on knowledge of the Devil's Canyon Bridge made him uniquely qualified to identify potential problems during the fatal inspection. His death leaves 4 children without their father and removes a key source of practical knowledge about the railroad's aging infrastructure. Junior engineer Michael Rodriguez, 29, loses his life just as his railroad career was beginning to flourish. Rodriguez's enthusiasm and fresh perspective had made him a valuable addition to the inspection team. His pregnant wife must now face single parenthood while grieving the loss of her husband in this preventable tragedy. The structural collapse destroys a 200-foot section of the Devil's Canyon Bridge, creating a gap that completely severs the transcontinental rail line. Twisted steel beams, concrete debris, and wooden planking litter the canyon floor across an area spanning several acres. The remaining portions of the bridge show signs of stress concentration where the failed section separated, raising questions about the structural integrity of the entire span. Environmental impact from the collapse includes contamination of the small stream that flows through the canyon bottom. Diesel fuel from the inspection team's truck, paint chips containing lead, and preservative chemicals from treated timber create potential hazards for downstream water users. The debris field also disrupts wildlife habitat in an area that serves as a corridor for desert animals seeking water. The regional economic impact becomes apparent within hours of the collapse as freight trains begin backing up at terminals throughout the Southwest. The Devil's Canyon Bridge serves as a critical link in the transcontinental railroad network, and its loss forces costly rerouting of traffic over longer, less efficient routes. Agricultural products, manufactured goods, and raw materials face delays that ripple throughout the regional economy. Railroad company stock prices plummet on news of the catastrophic failure and loss of life. Investors recognize that the accident will result in massive liability costs, regulatory penalties, and expensive infrastructure replacement. The Santa Fe and Western Railroad's financial position deteriorates rapidly as insurance coverage proves inadequate for the full scope of potential claims and business interruption losses. Community reaction to the bridge collapse and loss of 5 lives ranges from shock to anger as residents demand answers about how such a tragedy could occur. Local newspapers begin investigating the railroad's safety record and maintenance practices, uncovering a pattern of deferred maintenance and cost-cutting measures. Families of the victims receive an outpouring of community support while also facing the harsh reality of their financial situations. Federal investigators from the Interstate Commerce Commission arrive at the collapse site within 24 hours to begin their comprehensive investigation into the cause of the catastrophic failure. The investigation team includes structural engineers, metallurgists, and railroad safety specialists who will spend months analyzing every aspect of the bridge's design, construction, maintenance, and operation. Their mandate includes determining not only why the bridge failed, but also how similar failures can be prevented in the future. The investigation begins with a systematic documentation of the debris field and recovery of critical structural elements for detailed laboratory analysis. Investigators photograph every piece of wreckage from multiple angles, creating a comprehensive record of the collapse pattern. Key structural members are marked for removal and transport to materials testing laboratories, where sophisticated analysis can reveal the failure sequence. Metallurgical examination of the failed L7 lower chord member reveals the presence of fatigue cracking that had propagated through approximately 80% of the member's cross-section before final failure occurred. Laboratory analysis shows that the crack initiated at a rivet hole where stress concentrations and manufacturing imperfections created ideal conditions for fatigue damage. The crack had been growing for an estimated 15 to 20 years before reaching critical dimensions. Investigators reconstruct the failure sequence using debris patterns, witness accounts, and structural analysis. The evidence clearly shows that the L7 member's fatigue failure triggered a progressive collapse that spread throughout the affected span within seconds. Computer modeling, primitive by modern standards but advanced for 1967, confirms that the loss of this critical member would inevitably lead to total collapse of the bridge section. Expert testimony during the investigation reveals significant deficiencies in the railroad's bridge inspection and maintenance programs. Structural engineers testify that proper fatigue analysis would have identified the L7 member as a critical concern requiring detailed monitoring. The railroad's visual inspection procedures, while meeting minimum regulatory requirements, were inadequate for detecting the type of hidden damage that caused the catastrophic failure. Federal investigators examined maintenance records dating back to the bridge's construction in 1889, uncovering a pattern of reactive rather than preventive maintenance that allowed critical problems to develop unchecked. The records show that the railroad consistently delayed major structural work, opting instead for minimal repairs that addressed immediate operational needs without considering long-term structural integrity. The investigation reveals that warning signs of impending failure had been present for years but were not recognized or properly evaluated. Workers' reports of unusual sounds, Loose bolts and structural movement were documented, but not analyzed in the context of overall structural health. The railroad's inspection procedures focused on immediate safety hazards rather than the gradual deterioration that led to the catastrophic failure. Testing of steel samples from various parts of the bridge reveals that the original construction materials met the standards of their era, but contained impurities and manufacturing defects that made them susceptible to fatigue damage. Modern steel production methods available by 1967 would have produced materials with significantly better fatigue resistance, but the railroad had never considered upgrading the original structure. Analysis of loading records shows that the bridge had been carrying trains heavier than those anticipated in its original design, contributing to accelerated fatigue damage in critical members. While individual trains remained within the structure's rated capacity, the cumulative effect of decades of heavy loading had shortened the fatigue life of key components. The investigation determines that better load management could have extended the bridge's service life significantly. Weather data analysis reveals that wind loading on the day of the collapse, while within normal ranges for the region, contributed to the final failure by adding dynamic stresses to the already critical L7 member. Investigators conclude that the structure was so close to failure that almost any additional loading could have triggered the catastrophic collapse. The investigation's final report, released 18 months after the tragedy, concludes that the 5 deaths were entirely preventable through proper structural monitoring and maintenance practices. The report identifies multiple system failures that contributed to the accident, including inadequate inspection procedures, deferred maintenance, insufficient regulatory oversight, and lack of modern analytical techniques for aging infrastructure. Legal proceedings following the bridge collapse result in extensive litigation as families of the 5 victims file wrongful death lawsuits against the Santa Fe and Western Railroad. The lawsuits allege that the railroad's negligent maintenance practices and inadequate safety procedures directly caused the deaths of the inspection team members. Company documents revealed during discovery show that executives were aware of the bridge's deteriorating condition, but chose to minimize repair costs rather than address structural problems. Criminal negligence charges are considered by federal prosecutors, but ultimately not pursued due to the regulatory environment of 1967, which provided limited guidance for bridge maintenance standards. However, the Interstate Commerce Commission imposes substantial fines against the railroad for safety violations and requires comprehensive upgrades to all company bridges before freight operations can resume. The wrongful death settlements, while confidential, are reported to be among the largest in railroad industry history at that time. The 5 families receive compensation that helps secure their financial futures, though no amount of money can replace the husbands and fathers lost in the preventable tragedy. The settlements also include provisions for ongoing medical care for family members and educational assistance for the victims' children. Regulatory changes prompted by the Devil's Canyon Bridge collapse revolutionized railroad bridge safety throughout the United States. The Federal Railroad Administration, created in part as a response to this and other railroad accidents, establishes comprehensive bridge inspection standards that require detailed structural analysis rather than simple visual examinations. The new regulations mandate periodic load testing, fatigue analysis, and non-destructive testing of critical structural members. Industry-wide safety improvements include the development of bridge management systems that track the condition and remaining life of aging structures. Railroads must now maintain detailed records of structural modifications, loading history, and environmental conditions that affect bridge performance. Computer-based analysis tools, still primitive in 1967 but rapidly advancing, become standard equipment for bridge engineers. New technologies for bridge inspection emerge in response to the lessons learned from the Devil's Canyon tragedy. Ultrasonic testing equipment capable of detecting internal cracks becomes routine for examining critical structural members. Strain gauge monitoring systems provide real-time data about structural stresses during train operations. These advances make it possible to identify developing problems before they reach critical stages. The railroad industry establishes new standards for inspector training and certification, requiring formal education in structural engineering principles rather than relying solely on apprenticeship programs. Bridge inspectors must now demonstrate competency in fatigue analysis, load calculations, and modern testing methods. Continuing education requirements ensure that inspectors stay current with advancing technology and analytical techniques. Professional engineering societies develop new guidelines for managing aging infrastructure, drawing heavily on lessons learned from the Devil's Canyon Bridge failure. These guidelines emphasize the importance of understanding fatigue mechanisms, documenting loading history, and planning for systematic replacement of critical components before they reach the end of their service lives. The long-term impact of the Devil's Canyon Bridge collapse extends far beyond the immediate tragedy that claimed 5 lives. The accident serves as a watershed moment for railroad safety, forcing the industry to confront the reality that aging infrastructure requires sophisticated management rather than simple maintenance. The deaths of Martinez, Chun, Williams, Santos, and Rodriguez become a catalyst for fundamental changes in how America maintains its transportation infrastructure. Memorial services for the 5 victims draw hundreds of railroad workers and community members who recognize that these men died while performing essential safety work. The tragedy highlights the dangers faced by infrastructure workers and leads to improved safety equipment and procedures for bridge inspection activities. Fall protection systems, communication equipment, and emergency response procedures all receive significant upgrades following the accident. The families of the 5 victims establish a scholarship fund to support engineering students interested in infrastructure safety, ensuring that the memory of their lost loved ones contributes to preventing future tragedies. The scholarships specifically target students from railroad families, recognizing the unique challenges and contributions of transportation workers. Current bridge inspection standards throughout North America trace their origins directly to lessons learned from the Devil's Canyon collapse and the 5 deaths it caused. Modern bridge management systems use sophisticated computer modeling to predict fatigue life and schedule preventive maintenance before critical failures can occur. Non-destructive testing techniques that were experimental in 1967 are now standard practice for examining aging structures. The site of the former Devil's Canyon Bridge now hosts a modern concrete structure designed to current seismic and wind loading standards. The new bridge incorporates multiple redundant load paths that prevent progressive collapse even if individual members fail. A small memorial plaque honors the 5 men who died in the 1967 collapse, ensuring that their sacrifice is remembered by future generations of railroad workers. Safety culture changes within the railroad industry reflect the profound impact of losing 5 experienced professionals in a single preventable accident. Modern railroad companies invest heavily in predictive maintenance programs, structural health monitoring, and worker safety training. The philosophy has shifted from reactive maintenance to proactive infrastructure management, with the goal of preventing catastrophic failures rather than simply responding to them. The Devil's Canyon Bridge collapse demonstrates how seemingly routine infrastructure can harbor hidden dangers that threaten the lives of the very workers responsible for maintaining safety. The 5 men who died were experienced professionals performing their duties conscientiously, yet they fell victim to systemic failures in how society manages aging infrastructure. Their deaths remind us that safety requires constant vigilance, adequate investment, and recognition that the true cost of deferred maintenance can be measured in human lives. The technical lessons learned from this tragedy continue to influence engineering practice decades later. Fatigue analysis is now a fundamental part of structural design and assessment. Load monitoring systems provide real-time data about structural performance. Advanced materials and construction techniques produce infrastructure that is more resistant to the gradual deterioration that claimed 5 lives at Devil's Canyon. The human cost of the Devil's Canyon Bridge collapse cannot be forgotten amid discussions of technical improvements and regulatory changes. 5 families lost their primary breadwinners and emotional anchors. Children grew up without fathers, wives became widows, and a community mourned the loss of respected members. These personal tragedies serve as powerful reminders that infrastructure safety is ultimately about protecting human life and preserving families. Modern bridge inspection procedures honor the memory of Martinez, Chun, Williams, Santos, and Rodriguez by ensuring that no inspection team will again be surprised by catastrophic structural failure. Advanced warning systems, redundant safety equipment, and comprehensive structural monitoring make bridge inspection dramatically safer than it was in 1967. The deaths of these 5 men contributed to safety improvements that have undoubtedly saved many other lives in the decades since their tragedy. If this story about preventable tragedy and lost lives gave you insight into why infrastructure safety matters, leave your like and share with others who appreciate learning from fatal accidents so others might live.